I hope you are fine. So let me explain the simulation. So first we look the overall simulation. So this is main our solar panel with a grid connection, and the lower part is our connection to the battery. So I will explain each and everything to you, that how the simulation is working, and how the process. So let's start with these two blocks. So so you may know about the adhesion level of the PV array. So adhesion means the light that is imposed into the solar panel. So let me explain this part. The first graph is the adhesion level. So it is showing the maximum adhesion is 1000, and the minimum is round about 300, and maximum is 1000. So it means that it will start from 0 and it will approach maximum to the 1000. And it is also telling that at 1000 level our PV is produce maximum power, and in this point our PV is produce minimum power, and similarly at this point our PV is produce maximum power. So this is basically drawn the waveform for the whole day. Like if we start from 7 a.m. That after the sunshine, so it will start generating the maximum power, and the point occur when the panel producing maximum power. Let's suppose say at 2 p.m. or 3 p.m. is a time that a solar panel will generate maximum power. So at 6 7 p.m. Solar panels start reducing their power due to low adhesions, like low sun power. So the output power will be minimum. So the second graph is the temperature. So it is also showing that minimum temperature is 25 Celsius and maximum is 50 Celsius. So if we are doing research on the solar system, that we have to measure the different values of solar panel with respect to the temperature. So we have to consider the value of the temperature and different levels, in this simulation we considered it 25 Celsius and 50 Celsius. Let's suppose what happens if the temperature rise from 60 Celsius or 70 Celsius. Obviously it is not possible that temperature goes at maximum level, like above 100 Celsius or 70 Celsius. But how the solar panels will behave at a maximum temperature. So this is much important parameter for the simulating of the solar panels. So this is the two most important parameter. In the next section we will discuss about the PV array. The total solar panel is designed for the 100 kilowatt. So we have to choose the value of the solar panels accordingly. Okay. So we know that we have to connect the solar panels with the maximum with a grid connection. So we will select the solar panel module here. Here is the multiple solar panel modules with the specified ratings. So we choose SR30 5E WHTD. It is a series of the solar panel module. You can also search about that in the Google, that the what is this modules and the rating of these modules and each and everything, right? So in this system, we this module says that the maximum power that each panel will produce is 305 watt. It means that the one solar panel will produce 305 watt wattage. And if you multiply, let me multiply this one, and you will you will easily understand what is this. So each panel is our 305 watt. In parallel strings means that we have 66 panels which is connected in a parallel, like 1 2 3 4 5 6 7 8 9 10 11. So these are solar panels is connected in parallel, like 66 strings mean let me explain this one on the PowerPoint. I will explain this thing to you. Mm, yeah, this is panel 1. We will call it P1, and this is P2, this is P2, and this is P3, right? Similarly, these strings are connected, these 67 strings are connected. So this is our 67 string. Similarly, these are 5 strings, 1 2 3 4 and 5. Similarly, P1 here, P2 here, and similarly so on, and similarly so on. 1 2 3 4 5. So these are the 5 strings that is connected, and each panel is 305 watt, producing its maximum power. So as we also know that in the real life, the solar panel does not produce its maximum power all the time. Like it is mentioned 305, so it will approximately produce 250 watt in actual, and or 220 watt actual. So these are 10 to 15 minute times in the whole day that it will produce maximum power. Just 10 to 15 minutes in the whole day that the solar panel will produce only 305 watt. So let me explain the this one. Yeah, we have the each panel is 305 watt, and we have 67 strings. So we will multiply 67 strings. So, and we have 5 series string. You can see we have 5 series string. If we multiply by 5 here, so it will around about 102, like 100 102 kilowatt. So the whole system is designed with 100 kilowatt. Okay, and this is, you can also plot the PV character PV graphs here. So I think, yeah, there is a display IV curve and PV curve. So let me plot this one. Yeah, you can see this is the plot is showing. So here you can see the with the increase in the our excess is voltage, and this is our current, and we can see the relations of the PV characteristic, and here the power relationship with respect to the voltage. And you can also search you can also change the different modules and check the PV equation here. So with respect to the temperature, with respect to admittance, with respect to the one module, so you can take any of these. So let us move to the next part. Here is our boost converter. You really know it well. It is a basics part of the power electronics. So I think it is not to explain about the boost converter here. So what is the purpose of using boost converter here, right? So our solar panel will produce power, right? So our main aim is to give the specified voltage to our DC to AC converter, right? So in order to maintain the voltage level and extract maximum power from the solar panel, we use the two things here. One is MPPT controller. This is the MPPT controllers. Various types of the MPPT controller is designed, like increment conductance method, incremental method, and this is already designed MPP controller, and VSCs are already designed. So here what is the purpose of these two parameters? So let us suppose at the points occur when the solar panel voltage become reduced, like let us suppose it is 36 volt. Each panel is producing 36 almost like 36 volt. Let me check it again. Yeah, 64 volt. So it means that the boost let us suppose we need it here 100 volt, right? So our boost converter, what will do, it will try to achieve the voltage level of 100 volt to achieve this AC to DC converter to work properly. Let us suppose our solar panel producing minimum voltage, like in the evening at 6 p.m. or 5 p.m. So obviously its voltage level become low. So what will our MPPT controller do? It will try to change the duty cycle in such a way that it will keep the voltage level at the mm, at its desired level. So we will extract the maximum power from the solar panel. So this is the MPPT algorithm. So there are various algorithms like neural network algorithm, physiologic algorithm, incremental conductance method algorithm. So you can search about this. So before this I want to tell you that which paper I am following to to uh, to use, which is I use in this paper, in this I downloaded multiple papers here. Yeah, this one, and let me select the specified paper that I use in it. 45. Yeah, this one. So this is the paper that I follow. This is the modeling of the grid connecting solar PV using a MATLAB simulating. So here you can see a lot of equations, and I think I this is the model that I designed here. Yeah, this is one. This is a PV array, this is a boost converter, this is inverter control, VSC, and this is MPPT controller, and this is the out transmission line, and LC filter, and a load, and the utility grid. So the value may be different in our simulation. So let's move the further part. Here our DC voltage will convert into AC voltage, and it is fed into the transformer in the line resistance. So this is our line parameter, like inductance and resistance of the ohm. If you are familiar with the transmission lines parameter, like there is the capacitance, inductance and resistance of the transmission line, and also the types of transmission line: short, medium and long transmission line, and also the pi network and T network. And these are the all the parameter which is included in the transmission line. So you need to go for the theoretical part if you need details about that. So after that, it will fed into the 10 kVr, the our capacitor bank. What will capacitor bank do? It will it will keep the waveform smooth level. After the conversion of the AC to DC converter, it will make our waveform much smoother, and then it fed into the transformer. So our 260 volt producing 3-phase 260 volt producing by this inverter, and this is fed into a transformer, and transformer step up the voltage to 25 kV. And let us skip this part. I will move this part to next step. So this is our 5 kilometer feeder, and this is our 14 kilometer feeder. Let us consider this transmission line, that it is 5 kilometer. For our first load is 5 kilometer away, and our second load is 14 plus 5, 19 kilometer away. So this is our connection to the grid, and this is the 3-phase voltage source we have taken to produce the grid level. So this is our 30 megawatt load, this is our 2 megawatt load, and this is 2500 MVA is connected. So this is the overall part of the main simulation. So let us move what the flow of what will the flow of circuit. So flow of circuit start from there, from the solar panel. It will convert AC into DC from this part, and then this is fed into the grid. This is the simplest way to explain this one. So now move to this part. What I did in it, that let us suppose that our load is increased too much in the peak hours. Let us suppose in the 6 p.m. or 7 p.m. our solar panels stop producing the power, and we have to deliver the power to the grid. So we have the shortfall of the some wattage. So what we will overcome this. We have to connect the storage system in it. These two possibility of for the battery storage. One is to connect directly to the solar system, and other is connected to the grid. So it has own drawbacks and here, but I find that this by using this the system cost will increase, but this is the most efficient method for storing of the energy. So here you can see that a connection 20 kV bus. If we go into the transformer section, here you can see the parameter that our primary is 260 volt and secondary is 25 kV, and this will produce 25 kV at the secondary side. So here it will fed into the bus 1, and here another transformer which will convert 25 kV into 13.8 kV. It will step down the voltage, and it will fed into the AC to DC converter, right? And AC to DC converter convert AC into DC and store the battery. So in the off-peak hours, let us suppose our solar panel is producing maximum power, so it will charge the battery, okay. And in the high demand value, let us suppose increase the load in this section is much higher. Let us suppose I will put here, instead of 2 I will put here is 200 here. Okay, for your understanding, what will do, the load value become too much high, and our solar panel is not producing much power, and our grid is also not producing much power. What will happen? So so there will be change in the frequency in the system. Okay, so we will measuring the frequency and the power of the system in each and every step, like in each and every point frequency and power is measuring. Okay, I will explain you by graphically that how it will work. So for this purpose I use the another paper for the modeling of this one. So this is the energy storage system integration with the wind generation for the primary support in the distributed grid. So this is the paper that I taken, and here they use this algorithm. So I also added this one into your report. Okay, so this is the start, and it will measure the frequency. If the our set frequency is less than desired frequency, so what will do, it will discharge the battery, because our set frequency is, let's suppose, 60 hertz, and it will show 59 hertz or 58 hertz. So it means there is disturbance in our model, like we need more power to deliver to the load. So there will be change in frequency. So the battery will detect the change in frequency in the system, it will start discharging. So it will try to deliver power to the load. It will start converting DC power into AC power and start delivering to the 20 kV bus. And this is connected to the hour again. This is our connected to the load here. Okay, so yeah, this is connected to the again load, and is try to fed the power. Let me explain this by your no, this one, no, this one. This is your report, right? So I produce the result here because MATLAB will take time to run. Let me explain the sum graph here. So this is the main graph, and yeah, this is let's start from the graph here. This is the graph for the PV system. Here is our aridance level, which is I already discussed here, that we plot this the aridance level here, and same graph is showing here. And this is the temperature, which is 25 Celsius. We set it to minimum level, and this is the P mean, maximum power that solar power panel produce minimum, then goes to 0, then it's tried to maximum power 100 watt. Then similarly if we reduce like in this pattern, because aridance level reduce, similarly power will be reduced, and this level will be minimum power and will go to maximum power. Similarly V mean and duty cycle also taking in the same way. If you can see that our mean power is same, what does it mean? It means that our MPPT controller working fine. It is try to keep the voltage level at the maximum level, even with the low aridance level. Even with the low aridance level, it will try to keep the voltage at the maximum level. So also the duty level, you can say the same. Here is V graph with the IPV graph, the diode graph of the each panel. So I think it does not need to discuss. What is this graph here? This is the graph of the battery PMS that I attach here. Here you can see this is the controller that is controlling the frequency, and also go automatically to charge mode and discharge charge mode, right? So this is the graph that is plotted here. So here you can see SOC is the state of charge. Like initially our battery is 71.5 volt charge, right? 71.5% charge. So what I did in it, I take the only one graph here for the discharging. You can also take it as a discharging. So what is I did, I enter in it a much larger load. Let us go 200 megawatt. What will it did? It will cause the change in frequency in the system. So it will in discharging state, like you can say it is 71.5, then it will reduce 1.49, when 1.96, it is 71.494. It is reducing in this way. So also here you can see the discharging power. Charging power is approximately 0 because battery is in discharging state. Similarly, the voltage of the V bus. And this is the graph of the bus A system. This is the bus A, which is attached here. This is the bus A. Yeah, this is the bus. No, this is this is the bus. Is VABC and IABC is attached, and it measuring the power of the bus. So I put the graph of the VA and I. It is VABC and IABC. So similarly, if we go to this graph will show that the maximum power produced during the whole day of the PV panel, and this graph is produced from this section, this MPPT algorithm. You can also add this graph, but I think this is not necessary. And this is the PV graph, current, admittance and duty cycle, and this is also showing the maximum power produced by the PV panel and VDC. So in short, if we summarize the whole simulation, we will say that our main aim is to grid connected solar system. This is our grid, this is our transmission line, this is our solar system. Solar system producing DC power. We will use inverter here, and inverter is connected to the transformer, and transformer is connected to our load, and load is 25 kVA load. Let us suppose this is the industry load, like 125 kV, 25 kV is industry load. So this is the main part is of the simulation. The addition part is the battery here. So this is the whole simulation.